we are done with this. Right, once given this, you can see that the trace of A, right, will be equal to trace of B. Actually, we don't need this. We also can show this, right? Determinant of A. Let me see. Right, great equal to determinant of B. Right. Right. So with this, then we can have this property. Right. If A is greater equal than B. Any questions? Any questions? Actually, we can, like this well equality actually is very useful, right? You can see we can have some more inequalities similar to this, okay, which can characterize the relation of two matrices. Two matrices. So you can have more. And for more results similar to this well inequality. Okay. So A, B are Hermitian. And the first one is if so the first one is essentially is this well inequality. So let's write here again. Okay, so this is well inequality. And second one, so the first one says this is B is quite arbitrary, right? Here A, B, they don't have normal structure than Hermitian. Right? So B is general Hermitian matrix. So you see that this is can upper bound this eigenvalue, right, by the eigenvalue of A and B. Should be B, right? A and B. Right. Here needs its largest eigenvalue of B as an upper bound, and the minimum eigenvalue of B is a lower bound. Right. So now consider that if B is a rank 1 matrix, so now it's a ZZ Hermitian. Okay, it's a rank 1 matrix. So it's like a matrix is perturbed, right? It's perturbed by a rank 1 matrix. It's perturbed by a rank 1 matrix. Now, how about this? How's the eigenvalue? Okay, so this is called interlacing. Okay, so then the case if matrix is perturbed by rank 1 matrix, its case largest eigenvalue will still less than k minus 1 largest eigenvalue of A. Right? We know that this is true, right? Because lambda k minus 1 is not or less than lambda k. Right? If we order the eigenvalues from 1 to and so on. Right? And this tells you you perturb it by a rank 1 matrix still won't exist the lambda k minus 1's eigenvalue, and also will still larger than k plus 1's eigenvalue. So you perturb a matrix by a rank 1 matrix, the eigenvalue will be changed, but still in a range, okay, of the k is brother and his younger brother, okay， 就是在上面下面，实际上在那个区间里面 ，still in the interval。Okay. So then the third result is that if A now is perturbed by a B, okay, but here B is its rank is constrained by R. Okay. So now here is rank 1, right? Now here is B is ranked at most R. Okay, at most R. So now A is perturbed by a matrix is ranked at most R. Then it will be upper bounded by lambda k minus R of A and lower bounded by k plus R of A. Okay, so if rank the perturbed matrix is rank is R, then it will still the k's largest eigenvalue will still in the range k minus R largest eigenvalue and k plus R's largest eigenvalue of the original A, original matrix A. Okay, so that's this inequality tells us. Then the fourth one says if the fourth one needs assume that A, B are PSD. Okay, so it's not only Hermitian. Suppose A, B are PSD. Then if we consider J's largest eigenvalue and the K's largest eigenvalue of B, so A, B, we consider two different eigenvalues. One is J's largest, one is K's largest. Okay. Then this can be bound by the eigenvalue of A plus B. Okay, so it's upper bounded by J plus K minus N, largest eigenvalue, and lower bounded by J plus K minus 1. Eigenvalue of A plus B. Okay. The fifth one is about principles of math. So if we consider principles of matrix, so we define an index set, right? We define index set. Then we have these principles of matrix. We call it AI. Okay, so this AI is a R by R matrix. Okay, principles of matrix. This is R by R. So AI is taken from matrix A according to this index set. Okay, that principles of matrix. Then this AI, his k's largest eigenvalue, will no more than the k's largest eigenvalue of original A. Okay, but will be no less than the k plus m minus r eigenvalue of A. Okay, so these give a bound for if you have these principles of matrix. Okay, then the last one is that if we have a semi-unitary matrix, okay, then if you transform this matrix A using the semi-unitary matrix. Okay, now this becomes R by R matrix, right? Then it will be upper bounded the case eigenvalue of original matrix, but lower bounded by this. Okay, so we have these 6 results. So this one is most general. Okay, AB doesn't have any structure. Right? Then A plus B is eigenvalues bounded by this. Okay, largest and the smallest eigenvalues. If it's rank 1, this tells you that if it's perturbed by rank 1 matrix, then its case largest eigenvalue is still in the same range, within the same range. Okay, and this is if it's rank K. Okay, then the range is larger. Okay, because K minus 1 is largest eigenvalue, and K plus 1 is largest eigenvalue. And this one, if A and B PSD, then we can consider arbitrary JK, any 2 eigenvalues. Okay, and we can get its upper and lower bound by the eigenvalue A plus B. Okay, and this one is that if you take the principles of matrix, then it tells you its eigenvalue is always non-increasing. Okay, you take its eigenvalue will not increase. Okay, will not increase, but it's lower bounded by this, right, by the K plus M minus R eigenvalue. This one actually is an application of this. Okay, this one is actually an application of this. So any questions in understanding these properties? Right, this actually quite interesting. Right, these properties. So the first one we have proof. Okay, you can simply apply the coefficient we have shown in the Weyl inequality. This is quite easy. To prove the second one, we also use the coefficient because each one has 2 inequalities. Right? Has a lower bound, has an upper bound. So what I will only show one inequality. I will show this. Okay. I will show this. Okay, I will show this. I will show this. Okay, so and the other one is left to you as an exercise. Okay, the other inequality is left to you as an exercise. So let's see this. Okay, I want to show this. So we want to find the lower bound for A is perturbed by a rank 1 matrix. Right. Right. So it's A plus minus a rank 1 matrix, right? Rank 1 Hermitian. ZZ Hermitian, right? Then this by Cohen-Fisher, right? Is this Rayleigh quotient. Right? It's this Rayleigh quotient. right? So now we want to lower bound it by the A. So now here we want to eliminate this Z, right? And get a lower bound. Get a lower bound. So now we take the lower bound. Now we consider in here X is orthogonal to XW1 to WK minus 1, right? So here we artificially add one more. It is also need orthogonal to Z. Okay. So we add this. We add this. Right? Because we here compare, right? Look at the inside maximization problem. Now here X is orthogonal to this. Now we add one more Z here, right? So this becomes more restrictive, right? So his maximum value will be no larger than the maximum value of this, right? Because this is less constraint. So then here we get a lower bound, right? We get a lower bound. Okay, we get lower bound. And now X in the inside, X is orthogonal not only to this, also Z, right? So this can be removed because X is orthogonal to it. So this we will get 0, right? This quadratic form of ZZ formation will become 0, right? Because of X now is orthogonal to Z, right? So this is right. Okay, then I doing a trick. Okay, here I call this WK. I replace this Z by WK. And now here I add one more constraint outside, say WK equal to T, right? This is the same, right? This is the same as this, right? Now I introduce one more variable for WK and I say Z, and so X is orthogonal to WK. This is the same as X is orthogonal, right? This is equivalent. Right. Then next we drop this. We drop this constraint. So we drop this constraint, make WK has no constraint. Okay, so now here WK has a constraint equal to Z. Now I drop this. Okay. And the inside is still the same. Okay, now I drop this. And because here is minimization, right? As this constraint, then I'll drop it. I drop the constraint so feasible set become larger. This minimization. So the minimum value will be no larger than the minimum value, right? So here because I drop this constraint. So this fit now it becomes unconstrained. So this minimum value will be no larger than the minimum value of this with this constraint, right? You see that? Then what is this? This is lambda k minus 1. So lambda k plus 1. Okay. This is lambda k plus. Okay. So you see. So this is some trick we can learn. Okay. So these ideas, how they deal with this to get this inequality. Okay. So you can using similar fashion to prove this direction. Okay. This direction. So any questions in this proof? Then how about this one? Then this one is we don't need to prove. Why is that? Because rank, right? If B has rank no larger than R, right? No larger than R. So at most is R. So rank B is R. And it's Hermitian. So you can have SVD, sorry, you can have eigenvalue EVD, right? Eigenvalue decomposition, which is right. So here we can write as a R rank 1 summation R rank 1 matrix. Then you take one outside and combine A with the other R minus 1 matrix and one rank 1. So here R minus 1 plus lambda R UR Hermitian. Okay, I take one outside. Then we can bound lambda K A plus B, right? Lower bounded by the eigenvalue of this new guy, K minus K plus 1's eigenvalue of this guy, right? And you apply it again, you take one outside. So you can use the onion peeling, 就是剥洋葱那样一层一层 rank 1 一个。So you can add 1, add 1, add 1, add 2, add 3, add 4 to add R. Okay. So just apply this result here. Okay. R times, then you prove this result. Is that okay? You see that? Right? So this map B can be written as this part plus this one. Right? So we get that lambda K A plus the first R minus 1 component. Right? This new matrix, applying this, then is lower bounded by lambda. So this is lambda A plus B. It's lower bounded by lambda K plus 1 A plus the first R minus 1 component. Right? Then apply this again. Now it will create equivalent lambda K plus 2 A plus I take one rank 1 component outside. Again, right? Become R minus 2. Right? And grade equal to and so on. You apply this R times. So eventually you get lambda K plus R of A. OK， 就是把 B 都拨完了 ，OK， 都替完了这样，一次替掉一个 rank B 的一个 rank， 一次替掉一个 rank B 的一个 rank， 来替 R 次你就只剩下 A 了，对 ，OK， so you can so this is proved by just applying this for R times， 来 let's see that. Any questions about this? Okay, then let's see the fourth one. The fourth one is also the proof is also quite insightful. Okay, here we need AB is PSD. AB is PSD. Okay, AB is PSD. And let's check the fourth one. Okay, because A is PSD, so A is PSD, right? So as A, B are PSD, so we can have his EVD, right? And his eigenvalue or positive, his eigenvalue or non-negative, right? So A can be written as what's the ring? Okay, suppose it's this use doesn't matter. Okay, let's just consider all of them. It's M lambda I A U A I U A I commission, right? And B lambda I B, right? U B I commission, right? Right. And lambda 1 is the largest, lambda 2 is the second, right? So you see if now I let if I let this A suppose I define this A m minus 1, which contains, okay, let's define A m minus 1. We say this matrix contains the first n minus 1 component. Okay, n minus 1 component. So only the first, consider the first n minus 1. Okay, so here's n minus 1 component. Right, then this matrix can be written as is A minus his last rank 1. Let me see. Okay, I don't need to say this. Let's go straight directly. Let's define this. A j minus 1 is the first j minus 1 component. Okay. Okay, the first j minus 1 component. Then here we want to check out the j's eigenvalue of A, right, and also k's eigenvalue of B. Then you see the j's largest eigenvalue of A, okay, actually can be considered by considering A subtract aj minus 1. If aj minus 1 is subtracted from the A, right? So we remove the first j minus 1 component from A. So what is this? This will contain the component after J, right? So we'll have from J to M, right? Right, here we from J. Right. Then what is the largest eigenvalue of this matrix? It's lambda J, right? Because it's PSD. Because it's PSD. Okay, all these are non-negative. So all they are above zeros. Okay, they are above zeros. So for this matrix, right, its largest eigenvalue is lambda J. So which means lambda J, right, is equal to the largest eigenvalue of this new matrix, right? As A is PSD. Is that okay? Right. So A minus, I remove the first J minus 1 component, rank 1 component from A. So A becomes this, right? Then because all these are non-negative, so lambda J is the largest eigenvalue. 如果它不是 PSD 的话，那你这个 eigenvalue 可能是负的。那因为它还有 J 减一个0的 eigenvalue 就会排到前面去。OK， 所以我现在要是半正定的，所以这些活着的这些 eigenvalue 都会排在0的上面。OK， 所以第 J 个 eigenvalue 就变成是最大的。So that's the reason we need to PSD. OK, need to be a PSD. So all these are non-negative. OK, so if it's PSD, then the J's largest eigenvalue, OK, can be represented as A minus AJ minus 1 largest eigenvalue. That's I want to tell you. OK， 我把前面的 J 减1个都干掉了，第这个就是最大的，就这么简单。OK， so I remove the first J minus 1 component, rank 1 component from A. Then lambda J is the largest eigenvalue. So that's this equation says. Okay. Then similar, lambda KB, right? Lambda KB is the largest eigenvalue if I remove the first K minus 1 component from B. Right. Okay. So now we have an alternative way to represent this. Okay. Lambda J and lambda K. Right. So lambda J A plus lambda J lambda KB. Right. Now we want to prove it can be lower bounded by this guy. Right. Now we know we can alternatively represent as lambda 1, right? A minus AJ minus 1 plus lambda 1 of B minus BK minus 1. Right. Then by the Weyl inequality, the first inequality, okay, by the first inequality, you can check out your notes for the first inequality. Okay. This can be lower bounded, right? Like this. or you can say like this matrix plus this matrix. His largest eigenvalue is upper bounded by the largest eigenvalue of this one, the largest eigenvalue of this one. That's the Weyl inequality, right? We use the upper bound. So it's this matrix plus this matrix is upper bounded by the largest eigenvalue. Okay. Right, and now you put A and B together. And put these two guys together. And this is what? This is A plus B, right? Because now here we want to prove this. We want to prove this. Okay. This is, you see, this is A plus B perturbed by a matrix, right? And this matrix is rank. What is rank? What is rank? We don't know, but we know it's upper bound, right? It's no larger. This guy has a rank J minus 1. This guy has rank K minus 1, right? So his rank is no larger than J plus K minus 2. Okay, its rank is no more than J plus. Then we apply the third property, right? Apply the third property. The third property tell you, right, if it's perturbed by a rank, right, no more than this, then this one, right? The case now his 1, k is equal to 1, right? Will be lower bounded by k plus this number. Now his k is 1, right? Now this number is j plus k minus 1. K plus. Okay, so then this is apply the third result, the third inequality. Right? Right, so the first key is that we know if A, B are PSD, then his eigenvalue, okay, no matter which one, okay, can be always represented as the largest eigenvalue of A with some with component, right? It's removed. Okay, then here just apply the Weyl inequality and also the interlacing, right? Then we get this rule. So it's okay. Okay, so then let's see the fifth one. If now is we consider is a principal sum matrix. Okay, principal sum matrix. And want to prove this, or we want to prove that the case largest eigenvalue of A is low bounded by the case largest eigenvalue of any of these principal sum matrices, right? Any of these principal sum. So again, we use this Graham-Fisher right? Consider this quadratic form. Now we want to find a lower bound. Then the idea is quite similar. We prove in the interlacing. Okay, now we want to reduce this, right? We want to reduce this quadratic form because we want to find this lower bound, right? So then we want to find the quadratic form in terms of AI, right? In terms of AI, principal sum. So we want to reduce this from here, from A to AI, right? So we can introduce some constraints here. So the constraints will assume that the X is in the span and also I put the 2 norm here. So I add these constraints means that we now reduce the dimension of X. Here we assume X is in the span of EI1. E is a unit vector. EI1 means it's only in the I1 index, which is 1, others are zeros. Okay, so it's elementary vectors. So depending on the I, the index will be certain. So this means that we don't need to consider, here we restrict, not consider whole X, but we only take out those components of X that specified by this indexing. Take out that part. Okay, take out that part. Then this quadratic form, right? This quadratic form will be reduced, right? We'll see that this quadratic form will only involve the components in the principal sum vector, right? So by adding these constraints here, the objective value will become smaller, right? Equal or smaller, right? Because now here's the maximization part. We constrain it, add more constraints. Right? So as I say, then we can, right? We can rewrite this problem in terms of this reduced vector. So W1I here means that we only consider W1 and take out these components associated index I. Okay. Then here, right, everything is equivalent. X we only need to consider Xi, right? Now which is orthogonal W1. Right. And here, then we'll reduce to this, right? Or reduce to this, right? This is because these constraints, right? Given any W1, WK minus 1, but here, right? In the inside, we only actually these because of these constraints, we only need to, right? We only need to take care of those elements of X and W, right? In the locations specified. Right? Then you can call this, you can just use another notation we can call Wi, we call it Vi, right? And then we call this Xi, we call it Y. Okay. Then this becomes min, max, and here is this, right? Then this is lambda k a I, k a I, right? This is lambda k a I. So we get this results, right? This is okay. So you see the proof, the trick, the idea is similar to proving interlacing. OK， 所以这个证明呢，不是叫你要把这个证明记下来，你要去学的是它的这些 trick， 它怎么想。OK，and can be maybe become useful in other places. OK， is OK. Any questions about this? Right? If 5 for this is okay, then 6 is just a application of 5. Why is that? So 6 is just an application of the fifth inequality. Okay. In 6, we need to consider that U Hermitian A U is a semi-unitary, right? So this is R by R map. Now if I that U tilde is U and the U, okay, so this is U is this U. It's M by R. Okay, this is M by M minus R. So U is semi-unitary. We always can find a U perp, right, which spans the orthogonal component of U, right? So such that U tilde is unitary. Right? So U tilde is unitary. Right? So the k's largest eigenvalue of A is actually the same as the k's eigenvalue of U tilde Hermitian A U tilde. Because U tilde is unitary, right? This is similar. Two matrices are similar. Right? So this is unitary. It doesn't change its eigenvalue. Right? Right. Then you see the U tilde A U tilde is what? Is U Hermitian A U, right? U Hermitian A U per, right? U per Hermitian A U per Hermitian A U per, right? Then you see it, right? Then you see what? You see that U Hermitian U is a principal submatrix, right? So this is just a principal submatrix. So then by 5, you know that this is upper bounded. And this is by 5. Okay. So this is just by the fact that U Hermitian AU is a principal submatrix. If we construct the whole unitary matrix, okay, consider a transformation of using the U tilde, right? So you see this as a principal submatrix. So you can apply the fifth inequalities and you get results. Okay, so this is just a direct application of any questions about this? So then we are done with the PSD matrix. Any questions about this? So next we will we need to review this matrix norm. Okay, before going to the singular value decomposition, okay? Most general decomposition of matrix. Okay, so let's review this matrix norm. We have known vector norm very well, right? Right, vector norm, Euclidean norm, one norm, right? Infinity norm, P norm, Q norm, right? Have this Cauchy-Schwarz inequality, Holder's inequality, right? All these vector. Now, how about matrix? It's actually quite similar. Okay, matrix norm is a function here. In order to distinguish from the vector norm, I will use 3 vertical lines on each side. Okay, so sometimes I will use it. Sometimes I will use just 2 vertical lines, but I will mention that. Okay, if it is a matrix norm, but if you see 3 vertical lines here, I use is a okay, it's a matrix norm if which say for these actions, one is it must be non-negative, okay, and it is 0 if and only if A is a 0 matrix. Okay. Well, anyway, A is a 0 matrix. And so this is quite straightforward. If you scale the matrix by a scalar C, then it's just scale the norm, okay, in magnitude. Okay, scale the norm in magnitude. And the third one is triangle inequality, right? This is also the same as a vector norm, right? If A plus B, then its norm must be no larger than no. Okay, it's triangle inequality. Okay. The fourth one, which is also the difference from the vector norm, is that if you have A, B product, okay, 2 matrices, they are product, then A, B is bounded by, or here the not necessarily need to be a square matrix. Okay, can be n by n, can be non-square. Okay. Then A, B, okay, if its dimension is appropriate so that we can have their product, right? Then his norm is upper bounded by norm of A, norm of B. Okay. So satisfying these four actions, okay, is called matrix norm. Okay, it's a matrix norm. An interesting property is that some vector norm are also vector norms, matrix norm. Okay. Some vector norms are also vectors. So what do I mean the vector norm? Means that if you have a matrix, right? For example, one norm. If it's a vector, right? We take it as one norm. This is a vector one norm, which is summation, right? It's absolute value of its components. Now, then here, I mean, we apply this vector norm to this matrix, means we treat this matrix as a vector. You can think all his colors, right? You connect them into a long vector. Okay, put their colors, stack their color into a long vector. Okay. So for example, this is A1 to AM. Okay. AN. Okay. Then this is means that you stack them into a vector, then apply the vector norm. Okay, so this is I say, if we apply the vector norm to a matrix, means that you treat the matrix as a vector. So this is what I say, treat the matrix as a vector. Okay, so you stack his columns into a long vector, and you apply your vector norm to that vector. Okay, so if one norm, okay, if you apply it to this, which is will be absolute value of its summation of its right, the summation of absolute value of its entries. This will be you apply the vector one norm to matrix A, which is this, right? And Frobenius norm, this is called Frobenius. Frobenius norm is you apply the vector 2 norm. Okay, Frobenius norm is used to have this notation. Okay, is you apply the vector 2 norm to a matrix. Okay, so vector 2 norm, what's vector 2 norm? It will be is absolute value squared, right? Summation take a square. So that Frobenius norm. Frobenius norm is you apply the vector 2 norm to a matrix. Okay, vector 2 norm. You apply the vector 2 norm to the matrix. That's Frobenius. Then you can prove this by yourself. These are also are matrix norm. Okay, also are matrix norm. Also said by these four properties. It's also matrix norm. Now how about infinity norm? How about infinity norm? Infinity norm is taking the largest, right? Taking the largest elements of absolute value. Right, that's the infinity norm. If you apply infinity norm to the matrix directly, right, which is like this. But this one is not the matrix norm. Okay, infinity norm, if you apply it directly into a matrix, it's not the matrix norm. But if you multiply it n, then this one is a matrix norm. You can prove this by yourself. Okay, how to prove? Check these 4 properties. Okay, check these 4 properties. So you see that these 3 okay, so they are also matrices. These 3 are also matrices. Any questions here? You can check. But these all are quite obvious, right? Because these A, B, 1, 2, 3, they are also hold for the vector norm, right? So actually, you only need to check is the 4th one. Okay, only need to check is the 4th one. If 2 matrices, their product, whether can be bounded by, right, norm of A and norm of B. Any questions? Then there's a very important class of matrix norm. Very important class of matrix norm is called this operator norm. Operator norm. It's a very important class of matrix norm. So what is operator norm? It's also called, actually this is a better name. It's called vector induced. Vector induced. So what do I mean? This means this operator norm is induced by a vector norm. Okay, so you have a vector norm, then we can generate a matrix norm. It's something like, okay, we have vector norm, you can induce a matrix norm, and which this kind of norm is called operator norm. Okay, and how this is induced? So that be a vector norm. Okay, this is a vector norm, any vector norm. Okay, any vector norm be a vector norm. Then we define this matrix norm by considering this. Right, this is quite similar, right? This is like a quadratic form, right? But there's no square here. So you see, we given a vector norm. Then we consider this maximization problem. This maximization problem is objective function. Is A is the matrix, right? Given the matrix, A times X, and in terms of this vector norm. And also X is also subject to this vector norm equal to 1. Okay, so you're given a vector norm, then this value, this optimal value of this optimization problem, okay, is actually a matrix norm. Okay, so it's called vector induced norm. Okay, vector induced norm, or it's called operator norm. Let's give some examples. Okay, let's for example, I choose the 2 norm. Choose vector 2 norm, right? then this vector induced norm is what actually is the one we quite familiar with, right? So now if I choose two norm, right? Now here is two norm, is two norm. Then what is the induced matrix two norm? This is we know very well, right? We take a square, This is what? Largest eigenvalue, right? Largest eigenvalue. So you see the matrix two norm is a square root of the largest eigenvalue, right? Okay, I will stop here. Okay, so we will give some more examples. Okay, we'll give some more examples, and then prove that this indeed is a matrix norm.